Our next speaker is Professor Domoshnitsky, version of floquet theory for delayed differential equations. Sasha, you are welcome.
Okay, thank you very much. And let us start. My talk is floquet theory and stability of first-order delayed differential equations. Now, abstract. I propose a version of the floquet theory for first-order functional differential equation with delay. Equation with delay under standard conditions. We assume that A periodic function, tau is periodic function, standard condition on the coefficient that is not zero. And we obtain the floquet formula of solution representation. The use of the floquet theory opens new possibilities in the analysis of stability and ways for possible stabilization of process by delay feedback control. We propose, for example, an assertion of the following type. For our equation 1, with non-negative omega periodic coefficients and delays, there exists infinite number of intervals where n tends to infinity, such that in case of omega situated in one of these intervals, this omega is here. Equation 1 is exponentially stable. But the results of the sort open new possibilities in stabilization, which is interesting for. Let us continue. And what can I say? I can say that the foundation of floquet theorem for ordinary differential equation were proposed in two very known books. What is the main direction in last years? The main direction is connected with applications. Where application in epidemic models, which is very actual now, in biological models where we have seasonality. If we have in our model importance of seasons, we can consider equation with periodic coefficients, and for its analysis we can use floquet theorem. When we started to deal with application, it is clear that the memory appears as a result of our wish to use delay feedback control. If we want to use delay feedback control, we have to consider differential equation with memory. And mainly results there are for integral differential equations, and we can see them, for example, in the following papers: analysis of integral differential equation, floquet theory for integral differential equations, and for delay equations. We can know the following two books of Halana and of Hale, where they started to consider elements of floquet theorem. For delay equations, one of problems, one of difficulties in considering this problem is the infinite dimensional fundamental system. Because of this fact, in all works, authors considered only part of this theory. For example, they estimate floquet multipliers in the work, which is a very interesting problem. No, I cannot. Lusianina and has other and German mathematicians in this direction. Of course, Maleparet. In the following paper. What? I don't have enough. In the following two papers, authors considered delay differential equation as a model, but they use corresponding. We consider the following equation. Coefficients are periodic, and the following condition is fulfilled. What we can say about this condition? For what is our idea to consider this condition? And I want to know that is a particular case of our equation, one-term equation, and what is the idea? In real, many years it is considered that the case of constant delays is the most important case, the classical case, very well. But when we consider real problems, we see that most important in application is the following case, where delays control usually in the form x h of t, h of t, the t minus delay is tau of t, and what we see that deviation are wise constant functions. That is the most important case in applications. Why? No, let us consider, for example, medical problems. And what we see between two examinations, we use previous results of previous examinations, and we use it. We don't make analysis every hour, every minute, every second. And what we have, even among them, we have two variants. We have variants that the examination is made in hospital. For example, here in hospital, and we immediately know result, and we make examination in ambulatory conditions, in polyclinics. And we have results with delay, but we use this before our next examination. And here we have clinic examination at the point 0, at 4. And that is very clear. When we consider actions of technical equipment, we see the same combination. We see also we need to consider equation with such delays, and that is the most important case, in my opinion, for applications. And now, what is known for delay equations? We know the results of stability of exponentials, stability of Mishkins, and we know that this result is exact if we set instead of strong inequality, non-strong inequality. We have solution which does not tend to 0, and we know the following result of Yoneyama, Mishkis result in integral form. No, it is very known paper of Yenyama, but it is known that it is possible to obtain directly from result of Mishkis using transform of Ladas, Sfikas, Stavrolakis, for example. But that is one of the classical results of Yenyama, and we see the same inequality, 3/2. And what we know for equation with constant coefficients, we have that in this, if coefficients A tau satisfy this inequality, we have non-oscillatory and exponential, and equation is non-oscillatory and exponentially stable. If here, then equation is oscillatory but exponentially stable. And here, then this equation is oscillatory and amplitudes of oscillating solution can tend to infinity. What we want to obtain, we want to obtain that for corresponding t, we have opposite inequality, not less, more than 3/2. But the equation is exponentially stable, and opposite inequality to this, to the non-oscillation inequality, but equation is non-oscillatory. We consider this equation, and what is important formula of solutions presentation. And CTS is called the Cauchy function. Cauchy function is defined in the following form: as a function of t for fixed s. This is a solution of this homogeneous equation, satisfying initial condition at the point s, xs is 1, and with 0 initial function. And together, this is CTS is the kernel of integral presentation of solution. And our equation is exponentially stable if there exists two positive constants, and an alpha such that the following inequality is fulfilled. The coefficients and delays, of course, in our case, if we consider floquet theory, should be omega periodic, and we want to find solutions satisfying the equality. Okay, solutions. And what is important? It is important to describe lambda. If lambda is less than 1, we modulus of lambda is less than 1, we obtain stability of solution. And my first theorem is the following. Let condition 3 and 13, condition 3 that t minus tau it not less than 0, and 13 that all coefficients are periodic. Condition 3 that Asbelев, my teacher, said, чтоб не вылазило, чтобы запаздывание не вылазило за пределы нуля. Then the solution of equation can be represented in the following form, which is analog of classical floquet theorem. I don't, if lambda greater than 0, phi of t is omega periodic, and if lambda less than 0, 2 omega periodic. No, if 0, we have another presentation. I don't say about it in this talk. And what we can obtain. First theorem, which is actual estimate of lambda, and let a and t be omega periodic function. A is non-negative, tau t be measurable in such that t minus tau t greater than 0, h of t is the following, is non-increasing, and the inequality is fulfilled. Then delay equation is exponentially stable. We can demonstrate that 2 is exact bound, and 0 is, of course, is exact bound. Why? If a of t is 0, then solution is constant. but also from above it is exact. We demonstrate this. Let us try to compare our result with the known one, and consider this equation, and we take tau of t is t for t on the period, and it is continuous for others. Then h of t is 0, and we have inequality where instead of 3/2, 2. It is a better condition than in classical result of Mishka's union. The next theorem, we have equation, this equation with conditions. Condition 3, this condition, and condition 13 is the coefficients are periodic function. And as this equation is exponentially stable for every positive period omega, or at least there exists infinite number of intervals such that in the case of the period of the coefficient and delay situated in one of them, this equation is exponentially stable. Next group of assertion is connected with non-oscillation properties of this equation. Interval 0 omega is called non-oscillation interval. If every non-trivial solution does not have 0 on this interval, it is of t does not equal 0 on this interval. What we see here, what is important, that initial function is 0 here. I can make several remarks about non-oscillation of delay equation. Historically, the theory of delay differential equation can be started with the following equation, where we have to describe what we can substitute instead of xt minus tau when t minus tau is less than 0. And all others add the following equality. And but what is phi? If phi is a corresponding continuous function, which is called initial function, if we consider for any phi, possible phi, we have an infinite dimensional fundamental system. And what? No, for example, what consider the following equation on the interval 0, 1. And what we have? If we have the following function, initial function, we have this equation, and we can have every number of zeros on the interval 0, 1. And because of example of this sort, authors of all known books on the theory of oscillation and non-oscillation of differential equation with delay, non-oscillation is considered actually only as existence of eventually positive solution. There exists solution which is positive for sufficiently great large t, but not there were no definition of non-oscillation interval. It is considered that this non-oscillation interval does not exist. But when we did, my supervisor, my teacher, Professor Asbelev, was the first who proposed to consider initial function as 0 and it preserves us one-dimensional fundamental system for this equation, and we can obtain all we can obtain the analog of the floquet theorem. That is explanation of importance of this condition. We stay with one-dimensional fundamental system. The theorem let A of t be essentially bounded. Let A of t is essentially bounded, non-negative. Tau of t is non-negative. And the condition 3 is this one. And condition there is that the coefficients are periodic be fulfilled, and omega and 0 omega be non-oscillation interval of 1. Then lambda in presentation 15 satisfies the inequality. It means we can estimate the speed of tending to 0. Now, what is important in this condition, we have to verify non-oscillation, that 0 omega is non-oscillation interval. We have many results estimating non-oscillation interval. For example, condition A, condition B, and many others. We can see this, for example, in the following paper, and of course in the paper, my paper with Sergei Gusarenko, my friend. And now examples. Version of the floquet theory, and now we see importance of corresponding results obtained in our paper. And what we have, let us consider the following equation. Phi of t is here t, and that is two periodic function, and we can write its graph here. Oh, the green one. And we consider, together with this equation, we consider equation with delay tau of t, with this equation. Tau of t is phi of t on the period, and then we continue tau with period omega. No, it is clear that equation 19 and 22 coincides on the period 0 omega. What tau of t is the red one. You see the period is 3 here, and we on the period it is the same, but then we have it is different. What we can say about this equation? We can see that the deviation argument t minus phi of t present as carriers going up, ступеньки идущие вверх. And the solution of equation 19 is the following. That is 4 periodic functions. And what we obtained from our theorem, from floquet theorem, we obtained that for every omega, for every period omega, which is not equal to k, even the number, the equation is exponentially stable. Since modulus of lambda is less than 1. For even omega, the solution is periodical, is not exponentially stable. What we can obtain from here? From here, we see that in the inequalities in our one of our first theorems, 2 is exact. Why? Integral on this interval of a of t is integral of, it should be omega here, omega. And if omega is 2, we obtain the, for periodic, of course, solution and equation is not exponentially stable. Now, let us consider the following equation, 25. What we have here, we have h of t, deviation, as n minus 1 divided by 2. It means that we have a deviation of the sort 0, half, 1, 1.5, 2, 2.5, 3, and so on. And define phi of t according to our idea that tau of t should be omega periodic function. Now, using MATLAB, we obtain the solution. We obtain the solution. Here we start not from 1, we start 1 divided by that is 1 divided by 10,000. We have our solution start up. And what we have here, and here we, for example, for the case when we take omega is 15, we have this inequality for lambda. To cut this inequality, we see, well, we have this estimate for lambda. Now let us take this deviation, n divided by 10. And what we have, we see that we have two possible intervals for omega here and omega here, and we obtain exponential stability. Why? What the explanation is very simple. We obtain the solution. On each interval, we have a line. And what we have, that is a part of solution between -1 and 1. Here, we have a possible interval for omega, and here we have possible interval for omega, here and here. And in other zone, the solution is greater than modulus of 1, and modulus of solution greater than modulus of 1. And we only these two intervals are suitable for us. And if we have in equation h of t deviation of the following form, t minus 2, I said this sign, if t is less than 2, we take 0. And what we have very many intervals for omega. Very many intervals for omega. What we have, you see, we have here from 0 to 2, from 5 to 6, and here and here. We have intervals where omega can be in order to preserve exponential stability. What we have here, of course, we can construct Cauchy functions, and for equation of our types, if we have an equation with staircase going up, we can construct this function exactly. And to estimate the norm of this operator k, and it is clear that theorem let us equation exponentially stable, and the norm of the operator k is less than 1. Then equation with another delay is exponentially stable. What is important? It is important that if these two delays are close to each other, this term will be very small. And that is a possibility to obtain many new results. Many results about stability, even without conditions that невыладимо, but without невыладимо. And what we have said, if we can obtain the following result where A is the essential infimum of the sum, A with upper star essential supremum, and we can obtain the following inequality to obtain that positivity. And of course, if G of t and H of t, that is deviation for different delays, are small enough, we obtain that solution. What we can get, we can obtain for this equation, G of t minus theta of t. If delay is less than difference of delay is less than 1, we have exponential stability. No, results of this sort were obtained also in our paper with Gusarenko, and what we can obtain in a very simple case, the following example. We'll consider equation with this function with the deviation divided by the formula. No, H of t in other words, here is integer part of t, and we construct C of Ts, and it is clear that integral of CTS is not more than 1. And what we obtain, for example, the following picture. For standard condition, we have the zone between red line and T is equal to S. And in our condition, we have this initial triangles out of the zone. But we have many other pictures. If do I have time, I can demonstrate one more. Stop share and how to know. No, I don't see how to enter to another file, but I want to explain even without. We see есть объект, мы его хотим стабилизировать, но есть ограничения. Ограничения какого сорта? Длина запаздывания, то есть поступают данные о состоянии объекта, вот, например, через 10 секунд. И есть еще ограничения на тот коэффициент, который у нас может быть. Вот если мы включили наш прибор, например, единицу, итак, вот в этом уравнении у нас получается А равно единица, а запаздывание 10. Неустойчиво. Значит, что с этим делать, вот, когда неустойчиво? Значит, вот не было понятно. Если мы не меняем структуру, ввести там дополнительное запаздывание, да, можно ввести еще один член, как, например, вычитается там что-то, и все уже хорошо. Но в этом нет. Значит, что же делать? Что же можно тут предложить? Вот мы предложили вот эту идею сведения вот к уравнениям вот с таким вот запаздыванием. Но что с запаздыванием, которое, ну вот, говоря на сберовском сленге, не вылазит. Как это сделать? Оказывается, это все это технически хорошо реализуемое. Мы следим за запаздыванием. И вот мы на каком-то этапе, значение решения меньше там 10, вот меньше единицы, и вот там должно быть это омега. Как же определяется запаздывание? Да, мы просто построили эту формулу, как определить запаздывание в этом случае. И что? И ответ получается такой, что если мы построили вот такое запаздывание, то все, решение стало устойчивым. Причем вот на промежутке длиной 0 омега, это не обязательно, что амплитуда уменьшается. Амплитуда, у нас решение просто осциллирует. Да, на каких-то интервалах оно будет меньше единицы, на каких-то больше. Если оно осциллирует, то, конечно, существуют интервалы, где оно по модулю меньше единицы. Вот там надо брать период. Значит, вот если там берется период, все в порядке. И оказывается, что есть устойчивость за счет выбора вот этого вот омега. Ну вот, собственно, это все, что я хотел сказать. Я еще раз хочу поблагодарить организаторов. На Петровских чтениях выступаю первый раз, хотя в МГУ бывал неоднократно. Спасибо большое.
Okay, thank you very much, Sasha. What questions do you have?
Здравствуйте. Прошу прощения. Здравствуйте, Александр Исакович. Можно я прошу по-русски, чтобы было быстрее? Правильно ли я понял, что вот в одном из самых первых ваших слайдов там вы построили признак устойчивости, где практически не накладывали условия на величину запаздывания? Там у вас интеграл от величина должен быть был меньше 2, да? То есть получается при любом запаздывании практически есть устойчивость.
Понимаете, вот нет, не при любом. Это для запаздывания, которое не должно вылазить. Вот если запаздывание не вылазит, то да. Вот это вот требование-то остается. То есть вот там же 3/2, это точная граница, вот она для любого. Не может быть больше. У нас, вот понимаете, на последнем, кстати, слайде, вот видна эта красная зона наша, розовая зона, да, и видна зона D. То есть у нас вытаскиваются кусочки из вот этой зоны устойчивости, которая была бы построена вот по этому 3/2, по условию Мышкица. То есть где-то запаздывание наше меньше, чем не то, что чем 2, оно меньше, чем 3/2. То есть вот на каких-то зонах, вот в этой конкретной теореме должно быть, что наше запаздывание меньше даже, чем 3/2. То есть оно должно где-то там быть до единицы, меньше, например, даже, чем единица, например. Но вот, тем не менее, если мы берем интеграл вот на этой зоне, вот именно на периоде, то вот так получается.
Спасибо. Еще сразу один вопрос. А можно ли все это, есть ли у вас результаты, в случае, если А комплексное?
Нет, совершенно нет.
Спасибо.
Даже не представляю, никогда не занимался.
Okay, thank you very much. And other questions, please?
Можно,
Да. Можно громко. Саша, слышно нас?
Вот вопрос не совсем математический. У вас на некоторых графиках фигура 2, фигура 3, графики были такие, сначала красный, потом желтый, потом зеленый, вот эта перемена цветов, цвета.
Ой, я что-то плохо слышу.
Не слышите?
Слышу вопросы. Может быть, напишите по чату.
Сейчас, Саш, сейчас мы сделаем.
Или Ират,
Извините,
Так, слышно?
вопрос такой. У вас на некоторых графиках,
да.
У вас на некоторых графиках фигура 2, фигура 3. Вот идет график, он желтый, потом зеленый, потом красный. Вот это что-то замена цвета.
Это вот что. Это просто решение может строиться на интервалах. То есть вот вы знаете, вот эти запаздывания, вот которые кусочно постоянное отклонение вызывают, не запаздывание кусочно, а отклонение h от t, t минус запаздывание, оно же может строиться. Значит, мы берем просто на каждом интервале берем свой цвет. Вот мы построили на одном интервале, дальше мы берем там другого цвета, мы строим на следующем интервале, дальше третьего цвета. То есть это просто разделение по интервалам. На каждом интервале это отрезок прямой. Вот если у нас постоянный коэффициент, то это отрезок прямой будет. И вот мы строим. Значит, получается таким образом, мы строим на довольно длинном промежутке вот это вот решение. Мы проследим, чтобы оно попало в зону, вот, что омега надо выбирать таким образом, чтобы оно попало в зону, где решение от минус единицы до единицы. Вот и все. И поскольку у нас есть это решение на довольно длинном промежутке, то есть мои студенты составили программу, которая вылавливает, хотите 100 промежутков, хотите 1000 промежутков, нет проблем. Вот, но и на них они локализуют вот эти зоны, где решение от минус единицы единицы, значит омега вот может там быть. Если омега там, то вот эта лямбда оказывается по модулю меньше единицы, вот и решение тогда решение оказывается стремящимся к нулю как экспонент. Вот, собственно.
Спасибо.